Today's lesson is on empirical and molecular formulas. In a first-year chemistry course, this is probably, at least in my opinion, one of the most one-off lessons. And what I mean by that is this is something that once we learn it, we don't really use it for the rest of the year. So I'm not giving you permission to be like, cool, I'm going to peace out with this concept after this Unit 8 test. But I will give you some confidence that this is not something that you will have to kind of reach back and recall, at least maybe not until your spring final exam. But for today's lesson, you'll need your notes handout, obviously, your chemistry toolkit, your periodic table, and your calculator. But let's get into the real fun concept of empirical and molecular formulas. Okay, so empirical and molecular formulas. What is the difference between these two terms? An empirical formula is a formula which represents the smallest whole number ratio of elements in a compound. So the example that I have here is C5H11. Okay. When I mean I cannot reduce that ratio down, I cannot find some common number between 5 and 11 that I can divide both of those numbers by. I cannot do that. That is the smallest whole number ratio of those subscripts to each other, representing the ratio of carbon to hydrogen that I have. So that's called an empirical formula. Well, how is that different than a molecular formula? Let's see. A molecular formula is a formula which represents the actual ratio of elements in a compound. So the example for this one would be C10H22. So I want to look at these two things compared to each other. So a molecular formula, you notice it says an actual, okay? What I mean by that is that if I am looking and studying a compound and that is its formula, it is C10H22. I can also represent that in terms of the empirical formula for it, which would just be understood as the smallest whole number ratio. If you notice that C10H22, I can divide both a 10 and a 22 by the number 2 to get a smaller ratio that I cannot divide any further down. Okay, the C5H11, that empirical formula, is not the true formula for that molecular compound, but it does give you the ratio of the carbons and the hydrogens to each other. The true formula is the molecular formula. And some of y'all are like, wait a minute, I've heard this term lowest whole number ratio before. Yeah, you've probably heard me tell this when we've talked about ionic compounds. So note, you guys, ionic compounds, they are always represented as an empirical formula, right? That's why when we create a formula for an ionic compound, we make sure we reduce the ratio of ions to the smallest whole number ratio, right? So usually when we're looking at empirical formulas and molecular formulas, we're looking at covalent molecules, okay? We know that if I were to write the covalent molecule for this C10H22, I would want to see that. But mathematically, if we need to do something with this, we are okay knowing the empirical formula because that will actually represent the ratio of the elements to each other. So the concept of an empirical and molecular formula, and I think the reason why it's kind of like a one-off lesson for a first-year chemistry course, is that it specifically is used for the higher level kind of organic chemistry classes, specifically in some of the lab techniques that you'll be doing when you get to college because you're going to be a chemistry major. But for kind of just a first-year chemistry course, we don't get too deep into the OChem stuff, so this isn't something that is used on this lesson. I hate saying that. Anyways, so this is usually used for my molecular formulas, my covalent compounds. Amazing. So let's take a look here. I have a chart here with a list of some empirical formulas. And on the other side, it is what the molecular formula for those compounds would be. Okay, so I just kind of want to compare them side by side. Everybody in this column, you will have the smallest whole number ratio of each one of those elements to each other, meaning you will not see numbers that you can divide everybody by to get something smaller. So looking over here in the molecular formula column, it's like, okay, yes, I can see how these numbers are a little bit bigger. Yes, let's kind of look at this and make some generalizations about what we're seeing here. All right, one thing I want us to notice is that very first one. Did y'all notice H2O and H2O? You're like, well, those are the same. Yeah, an empirical formula can be the same thing as the molecular formula. We know that H2O is H2O. You have 2 hydrogens for every 1 oxygen. Well, that's already reduced down. So water's molecular formula is also its empirical formula. Or I think a better way to say that is water's empirical formula is also its true identity, its molecular form. So that's a possibility, right? They can be the same thing if you can't reduce the ratio down any further from that molecular formula. Next thing is that you're noticing that I'm scaling up from the empirical formula to the molecular formula by some whole number factor. So looking at this guy right here, CH2O, if I multiply all of those subscripts by 2, and keep in mind when you do not see a subscript, it's got a subscript of 1 because there's one of those, right? If I multiply them by 2, I would get C2, H4, O2 to get that true big molecular formula. This guy, pH2, if I multiply his subscripts by 4, I get P4 and then H8. And then this guy, you guys, this is the empirical formula for glucose. Because when I multiply all of its original subscripts by 6, I get C6, H12, O6. Okay, so I'm multiplying the subscripts from my empirical formula by a whole number to get to that true actual molecular formula. Okay, another thing that you can probably notice is that I could have 2 totally different compounds. Look at these 2 guys in the molecular formula category. They are totally not the same thing. They are totally different molecules that have different chemical and physical properties and have different purposes. But if I were to ask you, well, what's the empirical formula for them, it would look the same. So that is a possibility. So that's kind of interesting and kind of cool. All right, you're like, this is all a lot of words, Sabaka. What am I to do with this? How am I supposed to remember? This is how I remember, and this, man, I've been remembering this since I was 16 years old, okay, you guys? When I think empirical, I think imp or wimp, because that is the smallest reduced ratio formula that you can get. Versus when I think of molecular formula, I notice that molecular formula starts with M, so I think muscle. So that's the one that has the added muscle to it, which is the one that is created from some sort of multiple to those subscripts from the empirical. So I've got my imp, my wimp, very weak, small, my reduced down to nothing, or not to nothing, but the smallest whole number ratio is what we're reduced down, compared to my molecular muscle beefed up formula. So that is how I remember it, and I hope that that does help a little bit for you guys too. Okay, here's some other examples of our empirical imp, our WIMP formula, and our molecular, my muscled up formula. Okay, y'all, this slide is going to make you want to throw up. I'm sorry. We're going to read this, and then we're going to do some practice examples together, and you will be like, okay, now all of those words were not necessary, but I put them on here for you. So if you get confused, you can always go back to them. So the first step on how to find an empirical formula. Well, first of all, I can take any molecular formula, and I can take some information, percentages of elements, and I can from there create what the empirical formula for that compound is. So that this is what we are doing here. So it says step number 1, if given percentages of each element, assume 100 total grams of the substance and convert those percents to grams. Step number 2, now that you're at grams, you're going to convert those grams or convert mass to moles. Mass to moles. Y'all, it's a molar conversion. Yes. And that molar conversion is technically us dividing in grams by the molar mass of that element. So now I'm at moles. I'm at step number 3. At the moles step, I select the smallest value and I divide all values by that smallest one. And then step number 4, that is a step, and it looks like a lot here for you, but you don't necessarily have to have a step number 4, okay? If you have to use a step number 4, it says the results from step 3 will either be real close to whole numbers, or it will be recognizable as a decimal fraction number. Okay, so if any result from step 3 is some sort of obvious decimal fraction number, you must multiply all of those mole values by some common number to make them all whole numbers. Y'all are like, what is even happening here? When we get through the practice examples, this will make a whole lot more sense. But what I'm saying is that when you convert everybody to moles, or after you divide everybody by the smallest mole number, if you get something that's like a 0.5-ish, or something that's like a 0.33-ish, or something that's like a 0.66-ish, or a 0.25-ish, or a 0.75-ish, that is not anywhere close to a whole number, and you cannot call it a whole number and then move on. What I've got here is something that I've got to resolve. This is like a decimal fraction situation. So if you get a number that's close to 0.5, that's like a half of something, which then you'd resolve to make that a whole number by multiplying by 2. If you get 0.33 or 0.66, that's like a third or 2/3. Either one of those two choices you can resolve or make a whole number by multiplying them by 3. And then finally, if I get something that's close to a 0.25 or a 0.75, those are a fourth, 3/4. So I would resolve those decimal fractions by multiplying everybody by a 4. And when I say everybody, I mean everybody, even the ones who looked nice and whole when you were done with step 3. Okay, we got to keep things consistent. And then finally, step 5, I use these whole number results as subscripts and write the empirical formula, listing the elements in the order that were given in the problem. Okay, so this is a lot of steps. I feel like I talked a lot longer on that side than I intended to. Let's get to the practice examples because this is what I'm very excited for. Okay, so let's zoom in maybe a skosh and let's see. So that's all cute and fun, and you're like, how am I supposed to remember all of the steps because there's so many steps? And I agree, yes, there's lots of steps, but this is how you're going to remember it. You know me, I like easy ways to remember things. I've made a poem for you. It says percent to mass, mass to mole, divide by small, and multiply till whole. If you just sing that fun little song, maybe you can come up with a fun tune. I have not done that yet. Maybe I should. But then you will know all the steps on how to find an empirical formula. This little poem is basically all of these words up here that we have tackled together, okay? The one thing I want us to note is down here on step number 4. You may not need step 4. So I'm going to write this. You don't need step number 4 if you get whole numbers after step number 3. So I put a little star by this because sometimes you can even stop your poem. Percent to mass, mass to mole, divide by small. And then you are done, which is super exciting. One thing to keep in mind is this is going to be a lot of math. We're going to be doing a lot of numbers. Like it's the most numbers you've probably ever done in my class. But the cool thing is that I actually don't have to worry about sig figs for this because the end result or my answer of what I'm trying to get to is a chemical formula, a certain number of C's and H's or whatever elements from the periodic table. It's not a mathematical measurement or a numerical value. So the main thing is that there's no rounding issues, but you don't want to chop off the rounding for your numbers until you get close to the end, because what we're looking at here specifically for step number 3 is we're looking for after step number 3 for stuff to be not clear-cut whole numbers to where we will let us, or that will let us know that we do in fact need to execute step number 4. Okay, lots of talking again. Okay, here we go. So let's do the first practice example. It says, find the empirical formula of a compound which contains 54.93% potassium, 38.73% boron, and 6.34% hydrogen. So I'm finding the empirical formula, the EMP formula, meaning I want to know what the lowest whole number ratio is between the potassium, the boron, and the hydrogen in this compound that only contains those 3 things. So the first thing we do is percent to mass, mass to mole, divide by small, blah, blah. Percent to mass. What does that mean for me? Are y'all ready for this? You're going to love this. Percent to mass. Okay, how do I turn a percent into mass? Well, this, obviously, if you add all 3 of these percentages up, you will get to 100%, right? Let's just say, theoretically, we have a sample that is 100 total grams of all of these elements. Well, in a 100 total gram sample, I would have 54.93 grams of potassium and 38.73 grams of boron and 6.34 grams of hydrogen. Y'all, we just did step number 1 in our brain. Isn't that amazing? Just by deciding this is out of a sample of 100 grams to where those things are now, not percentages, but grams. Okay, so we're going to write that on our paper here, but let me show you. We're going to set up our empirical formulas to kind of have a little order of our first element in the math work for him, the next element and all the math work for him, and then the last element and all the math work for him. So I like to kind of set up a little space to go. So my first element that they said we have is we have some potassium. So we're going to work through some potassium information here. And then midway down, we're going to work through some boron information. And then closer to the bottom, we're going to work through our hydrogen situation. Okay. So our first step, percent to mass. Let's write those masses now next to whatever element they represent. So we said we had not 54.93%, but 54.93 grams of potassium. we had 38.73 grams of boron, and then we had 6.34 grams of hydrogen. Okay, that was it. Percent to mass. That was not too terrible. We were ready for the next step. Percent to mass, mass to mole. Mass to mole. I'm going to convert that mass in grams to moles. This is molar conversions, you guys. It is a one-step process. You are super excited. But in this step, going from mass to moles, I need to execute and use my molar mass from the periodic table, which lets me know there's a certain amount of grams in each one of these elements that are equal to 1 mole. 1 mole. Yes? Okay, so I'm on periodic table. Let's find him. This sounds good to me. Potassium, 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 potassium. His decimal number is 39.10. Boron, 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 boron. His decimal number is 10.81. And then finally, hydrogen, his molar mass is 1.01. Okay, and looking at the way I've oriented that conversion factor, this will give me the ability to cancel grams off on top and on bottom. And so the result of this conversion for each one of my problems will be giving me an answer in moles. So I got my calculator. I'm ready to go. Okay, so my first calculation for potassium, we would have 54.93, and I'm going to be dividing it by its molar mass of 39.10. Yes? Let's see. Okay, cool. So that is equivalent to 1.4. And you were like, okay, sig figs ready to go. Boo, boo, boo. Remember when I said it does not matter on rounding here. But you're going to need to write something down because we need to kind of keep an idea of what these values we're getting for each one of these elements. And you cannot possibly do that in your brain. So I like to say, since it doesn't matter for rounding, don't get too excited and like chop off this number too short because we need some amount of working room with these numbers to figure out things like, well, who's the smallest out of all these numbers I've written down? So what I like to say is I like, write 3-4 numbers past the decimal and just call it a day. So I'm going to write 1.405. And I'm not even going to write moles here. You're like, oh my gosh, she's not showing units. Remember, end goal here. End goal after all this process is to create a chemical formula. So I'm just now into straight numerical mathematical mode. And I'm like, oh my gosh, you guys are going to just love it when I say, you don't have to write units. You don't have to do sig figs. Congratulations. So embrace that, even though this may look like a lot of work for us. Okay, that was a lot of talking. Next up, my next element we said was boron. So boron, we're going to take his 38.73 divided by 10.81, right? Is it 81? Yes. Okay. And so my answer, once again, I'm not rounding. Give yourself some amount of numbers here that you can work with for the future steps. Okay. And then finally, I've got my hydrogen, 6.34 divided by 1.01. And so hydrogen, I'm getting about 6.277 moles. Okay. Y'all, we have done this. Percent to mass. Mass to mole. What's the next step? Divide by small. So what I'm going to do is out of all of these numbers that I have gotten here, I'm going to see which one is the smallest number that I see. It is that one. I'm going to divide all values by this smallest number. Yes? So I'm going to say divide by 1.405. Divide by 1.405. Divide by 1.405. And that's going to equal something. Yes? You're like, oh my gosh, where are we going with this? So we're now dividing by small, step number 3. Y'all, for this potassium, guess what? Itself divided by itself is going to be a 1. For the other ones, I need to grab my calculator. Okay, so I go 3.582 divided by 1.405, and I get, all right. So let me tell you that the result, meaning what you get after the divide by small step 3, is you are hoping to see whole numbers or something that's super close to a whole number, okay? If you do not see something that is super close to a whole number, meaning if that was like a 2.98 something, that's pretty much a 3. I would write a 3. Or if that was a 2.02, that's pretty much close to a 2. I would write a 2. What I have here is like 2.5, you guys. That is not anywhere close to a whole number. Specifically, it is close to, ding, ding, ding. Remember when I mentioned this stuff? This represents a half. These represents thirds, a third or 2/3. These are in fourths. I've got kind of a half situation that I'm like, oh gosh, I probably am going to have to execute step number 4 here. But anyway, let's write down what our calculator told us. So this is roughly about a 2.5. So I'm going to write 2.5, 49. And then finally, my last guy, 6.2. Cannot see. There we go. 6.277 divided by 1.405. Please be a whole number. Please be a whole number. Oh, that is not close to 4. That is not close to 5. That is pretty much 4.5. Oh my gosh, you guys. It looks like we're going to have to execute step number 4 because I did not get basically whole numbers here. Step number 4 says I need to multiply all values by a number that would make all of these a whole number. So we talked about these looking like halves of something. Well, to resolve a half of something, you multiply it by 2 times 2 times 2. I have to do it to all of them. Oh, but he's whole number. I don't care. I've got to take care of all of them, treat them all the same, right? So everybody here is getting multiplied by a 2. And I'm going to underline this and kind of star this. Because what we are doing here is a specific thing for step number 4. We did percent to mass, mass to mole, divide by small, and boom, we did not get whole numbers here. So now we are multiplying them till they are whole. So obviously 1 times 2 is going to give you a 2. 2.5 times 2 is going to give you a 5. And then finally, 4.5 times 2 is going to give you a 9, okay? So if you wanted to type that out in your calculator, you totally can. I thought that I would, if I were doing that, I would be bored. So this is the end goal, is to get these whole numbers. And you're like, great, what? How is this an answer? Well, it is not, but I have achieved all of this stuff so far. These are now the subscripts for these respective elements in my empirical formula. So since I have run out of room here, I'm going to write it underneath here. I have got how many potassiums? 2. K2. I've got how many borons? 5. B5. And I have got how many hydrogens? 9. So H9. So here is my empirical formula for this compound. And it's empirical because I cannot further divide 2, 5, and a 9 all by some common number to get something smaller. So here's, I know it is a lot of work just to get to this, but it is kind of fun because it's a cute little strategy of percent to mass, mass to mole, divide by small. And if you don't get whole numbers after that divide by small step, you need to multiply them till whole. Okay, let's do one more example of this before we go back into learning about my molecular formulas, the muscly side of this lesson. Okay. Says, find the empirical formula for a compound which contains 26.8% tin, 16% chlorine, and 57.2% iodine. All right, percent to mass, mass to mole. Okay, percent to mass. First of all, we have a tin. And we have a chlorine. And we have an iodine. So my percent to mass, let's just make those percentages mass. 26.8 grams. And then we have 16.0 grams. And then we have 57.2 grams. Okay, we did it. Percent to mass. Next step, mass to mole, which means I'm going to utilize the molar masses of each one of these each one of these elements to figure out how many moles that original value is. So tin's molar mass, let's find him, is 118.71. So that's how many grams are in a mole, right? Chlorine's molar mass is 35.45 grams in every 1 mole. And then finally, iodine's molar mass is 126.90. 126.90 grams. Okay. Percent to mass, mass to mole. All right, so let's see what we get from our results for doing step number 2. For my tin, I got 26.8 divided by 118.71, and I get, there we go. I get 0.2, okay. Do not round, very, very short, but the rounding does not matter at the end, but we do need to have a little bit left, right? So I'm going to say 0.226. That sounds good to me. Okay, now we're going to be doing it for the chlorine. So I'm going to have 16 divided by 35.45. Okay, that value is 0.451-ish. And then finally, iodine, I have 57.2 divided by 126.9, and I get 0.451-ish also. And some of you are like, oh my gosh, I see halves, I see halves, I see quarters. This is a very, very common thing that I typically see every year. The most common mistake on these is y'all don't work through the entire rhyme and you start forgetting step number 3 because you're getting excited and want to multiply these things by 2 or 4 or whatever, okay? So we did percent to mass, we did percent to mole. I still have to what? Divide by small. I have got to do that. Well, who is the smallest? It is that guy. So I have to divide everybody by 0.226. And after this step, that is where I am looking for hopefully some whole numbers and looking for specific decimal fractions if I have them. So for the 10, his is just a 1. Let's figure it out for the other ones. So let's see, 0.451 divided by 0.226. Let's see what we got here. Okay. Y'all are like, that's not a 2. Y'all, this is what I mean. That is basically a 2, okay? That is not close to a 1.5. That's not close to a 1.25 or 1.75. This is basically your calculator screaming at you, be like, this is a 2. I am a 2. Call it a 2 and move on with your life. So we will be doing that because that is extremely close to a whole number. And these are basically the same calculations, so I can be smart here and I can be like, okay, that will give me something that's roughly a 2. Oh, looking at this, y'all. So we did percent to mass, mass to mole, divide by small. I do not have to multiply till whole because they already whole after step 3. So congratulations, these are your subscripts, right? I have 110, which means I do not have to write a number. I have 2 chlorines, and I have 2 iodines. So this is the empirical formula for this compound. So for this one, I didn't need step number 4. And put a big smiley face because that makes you feel super excited. All right, so that's my empirical formulas. Okay, we're going to go back to the lesson and we are going to finish off with some molecular formulas. Okay, a molecular formula, as a reminder, molecular muscle is either the same as an empirical formula or it is some whole number multiple of it. So to determine the molecular formula, you must know the compound's empirical formula, meaning what is its whole number ratio of itself, and the mass of the molecular compound. You were like, that is a lot of words. I do not know what she's talking about. Work with me here. All right, just like last time, I've given you some steps. We're going to talk quickly through the steps, and then we're going to do a practice example, and you'll be like, oh, okay, this was a lot less complicated than that slide with all the how-tos said. So for finding that pumped up molecular muscle formula, step number 1 is you're going to calculate the molar mass, which you're like, oh yeah, molar mass is my periodic table of the empirical formula. That will be provided for you. And then you're going to divide the given molar mass of the molecular formula by the mass of the empirical formula to get a whole number multiple. And then you're going to multiply the subscripts of the empirical formula by that number to get to the subscripts of the molecular formula. You were like, what is even going on here? Okay, this can be summarized with simply the following equation. To execute and find a molecular formula, you need to figure out what multiple you need to multiply all of the original subscripts by the empirical formula with to get the true actual pumped up muscle formula. Okay, so you will take the molecular formula's mass and divide by the empirical's formula mass to get a whole number multiple there. Okay, so let's do the first example together and let's see if we can handle this. So yeah, here's the equation, and y'all are like, that is even a lot of letters of the alphabet for that equation, and I agree with you. So you will see me a lot of times abbreviate molecular formula as MF, mass, and then the empirical formula on the bottom is EF, mass. This is your goal. You need to find these two numbers, okay? And guess what? Half of it will be given to you. That top number is going to be given. That bottom number, you're going to need to calculate. So calculate from EF, okay? This top number is going to be your bigger number, and this bottom number will be the smaller one. So I find that to be helpful because you're like, I don't remember which one goes on top and which one goes on bottom. It's the big one because the whole end goal of this is we want to get a whole number and not something that's less by 1. Okay, so it says the molar mass of a compound is 181.5 grams per mole and the empirical formula is C2HCl. What is the molecular formula? You were like, what is even going on here? If I see they're asking me to solve for the molecular formula, the first thing I write down on my ding-dang paper is MF mass over EF mass. And you're like, I need to put numbers there. Okay, molecular formula mass. Remember I said that is always given to you. Y'all, they told me the molar mass of the compound of whatever this compound is. We do not know what it looks like. It's that. That's the molecular formula mass. We love that for us. So I found my top number, 181.50 grams per mole. Yes? You're like, cool, that's the only number you've given me, so where am I going to find a bottom number? Remember I said, y'all, you need to calculate what the molar mass is of the empirical formula. Did they give you the empirical formula? They sure did. Can I find molar mass? I sure can. So my empirical formula is molar mass is going to be 2 carbons, 1 hydrogen, and 1 chlorine. So I have my calculator. I have my periodic table. I'm ready to go. We have carbon. His molar mass is 12.01. 12.01. Uh-oh. Oh, I missed the decimal. 12.01, and there were 2 of them, so I multiply by 2. The next element I have is hydrogen. Hydrogen's molar mass is 1.01. 1.01. I only have 1 hydrogen, so that's it for him. And finally, my last element is chlorine. And chlorine's molar mass is 35.45. 35.45 equals. So there's my empirical formulas. Molar mass, 60.48. And remember, the units for molar mass are grams per mole. So that's the number that goes on the bottom. That's not too terrible. 60.48 grams per mole. Yes? Amazing. So we are ready. We are like, cool, I can divide. That sounds super fun for me. 181.50 divided by, from the answer that I just calculated above, the 60.48, I get, you're like, okay, what am I doing here? The whole purpose of this just little fraction, this division step, is to get a whole number here. Awesome. That's a 3. So just like our empirical formulas where we were like, we don't care about rounding because the end goal here is to create a chemical formula. That's the same thing we're doing here. We just need to get a whole number to let us know what? Oh, that's how much I need to multiply the subscripts of the empirical formula by to get what muscled up version of it actually is in this true compound. So it's a 3. So that means I take my empirical formula of C2, HCl, and I'm going to multiply it by 3. C2 times 3 is C6. H times 3 is H3. And then finally, Cl will be Cl3. So this is my molecular formula. So the molecular formula, once again, is the muscled up version of the empirical formula, which was provided to me, right? All I had to do is figure out what that empirical formula mass was and then divide the given molecular formula's mass by it to figure out what multiple I had to multiply everybody by. Amazing. So you're like, oh gosh, that is so easy. I love that when it is easy for us. So here we go. Here's another example. You're like, I'm so ready for this again. Find the empirical formula. Uh-oh, I thought we were doing molecular formulas. Oh, this is a double step problem. You're going to love this. It says find the empirical formula for a compound containing only carbon and hydrogen if it's known to contain 84.21% carbon. If the molar mass is 114 grams per mole, what is the molecular formula of this compound? They are asking me 2 questions here. They are asking me the empirical formula. I need to find that. And then they're asking me, what is the molecular formula? I am asking you to provide 2 formulas, an empirical and molecular. And you're like, oh gosh, this sounds terrible. Well, considering my molecular formula math calculation has me needing to know what the empirical formula is to get something on the bottom, I've got to do my empirical formula, percent to mass, mass to mole, divide by small, multiply to a whole. I've got to do that first. You're like, okay, amazing. So we're getting ready to go. We got percent to mass. We've got some carbon here. Y'all are like super excited. Percent to mass for my carbon. I've got 84.21 grams percent to mass for carbon. And then, I do not see, what is going on here? I do not see any other thing. They tell me I have hydrogen also in this, but they did not give me the percentage for hydrogen. I am super mad about that. There's no way I can solve this problem. We can be smart, and I think we can, right? If there are only two things in there, and one of the things makes up 84.21%, how would I figure out what percent the other guy makes up? So if I can look at this, I can say, therefore, the percent hydrogen, you can subtract from 100. So 100% minus 84.21%. Yeah? And that should give me the percent for hydrogen in that compound. Or it will give me, assuming I can type things into my calculator, which I've struggled a little bit with today. And so we will see how successfully I can work through this problem. Amazing. So that's the percentage of hydrogen in the compound. 15.79%. So boom, there's your grams of hydrogen, right? 15.79 grams. Percent to mass, mass to mole. So for every 1 mole of carbon, I have 12.01 grams according to my periodic table. For every 1 mole of hydrogen, I have 1.01 grams according to my periodic table. Okay, that was percent to mass, so we're going mass to moles. Now, this is what we're figuring out. 84.21 divided by 12.01. And I got, remember, give yourself some numbers here. I always like to take it out to 3 places past the decimal. Cool. My next one for hydrogen is 15.79 divided by 1.01. See what we get, And we got, wow, 15. Wow. It's a big number. That's okay. Cool. Sure. Okay. Percent to mass, mass to mole. Divide by small. That one is the smallest number. So I'm going to divide everybody by the 7.012. So 7.012 divided by itself is a 1. We know that. Let's see what we're going to get from this. And this is where we're hoping that we get whole numbers. But if not, we know how to handle them with the decimally type fractions. But let's see if we can get a whole number. 15.634 divided by 7.012. Cool. Okay, that's not close to 2 at all. It's also definitely not close to the next number. Next to it, it would be 3. It is like 2. What decimal fraction does that look closest to? Is that like a third or a half or a fourth? That's looking like a 2.25-ish or 2 1/4 to me. So I'm going to say, oh my gosh, 2.23-ish, or you know what? At this step, it doesn't even matter because the point of this is for us to see what we got to do to multiply things until we can make them whole. So I'm looking at this. I'm like, oh, good. So that is a fourth. I'm going to multiply everybody by 4. Right? So this number times 4 is going to give me 9. And 1 times 4 is going to give me 4. Okay? So we did our empirical formula. Percent to mass, mass to mole, divide by small. And then because we got this business here, we had to multiply everybody until we were whole. Okay, but those are the subscripts of my compound. So my carbons, I have 4 of them. My hydrogens, I have 9 of them. Okay, that was a lot of work. But now we have our empirical formula. And so we can now execute what the molecular formula is. Well, first of all, they asked what the empirical formula. That was an original question they asked. So we boxed that off just so they can see it. And by they, I mean me, because I'm the one grading your papers. So now I'm like, okay, now I can find the molecular formula by executing this fraction. My molecular formula, mass, over my empirical formulas, mass, right? The molecular formulas, mass, they will give to you. There was another number up here in the problem. They told you that's the molar mass of that molecular formula. So that's my molecular formula, mass, right? 114 grams per mole. Yes. And now to find the empirical formula's mass, I am going to grab my calculator and be like, okay, well, what's the molar mass of 4 carbons and 9 hydrogens? So 12.01 is the molar mass of a carbon, and I had 4 of him, so times 4. And then 1.01 is the molar mass of hydrogen, and I have 9 of him, so times 9. So my answer, my empirical formula is molar mass, and if you want, you can write it underneath here, not because I need to see it here, but that can help remind you when you're looking back at these notes where you were getting that number from that we were about to put here down on the bottom. You can be like, oh yes, it came from over here that I had to find from the empirical formula, which I also had to find in this problem. Okay, lots of words, Sabaka, get on track. Okay, so 15.13 grams per mole. And remember, the point of this step is to get to what number do I need to multiply all of the subscripts of this empirical formula by to get that muscled up molecular formula. Okay, so I got, what is it, 114? 114 divided by whatever that answer was that I solved for. And I get, what multiple whole number is that? That's a 2, right? So that lets me know that I have to multiply my original empirical formula's subscripts by 2 to get the molecular formula, which will be C8, H, 9 times 2 is 18. Okay, so these are the double step type problems where even though this strategy for finding a molecular formula is very simple, if you do not have an empirical formula to begin with, you cannot get much farther than you can't even start the problem, right? Okay, so we got to find our empirical formula first. But the main takeaway from this is those rhymes: percent to mass, mass to mole, divide by small, multiply till whole for your empirical formula. And then molar mass, or molecular formula's mass over empirical formula's mass to get whatever multiple you need to multiply. I've been saying the word multiply and multiple like way too many times for me today. But to get your molecular formula. So that is a real fun strategy on kind of creating your own formulas. It's very useful to know the subscripts of each one of the elements in the compounds for us to understand the ratio of elements we have to each other when working with these chemicals.